So the subject of today's lecture and of tomorrow's lecture is an important class of groups and an application of the theory of induced characters to this class of groups. There is a result for this class of groups that as far as I know, has only been proved so far using characters, in particular using induced characters. So what's this class of groups? It's the class of groups called Frobenius groups. There are two possible definitions of Frobenius groups. So we'll start with one, and then we'll prove that this is equivalent to another. So the first definition of Frobenius groups, so definition number one, says the following: let omega be a finite set. Actually, you could have a more general theory which covers infinite sets, but we'll stick to finite sets and subgroups here, because it's we want to apply characters of finite group. So let G be a finite set, and let G be a subgroup of the symmetric group on omega. So this is the group of all permutations. So note, since G is a group of permutations on omega, G acts on omega, but it acts faithfully, meaning every element of G is a permutation. It's not just that it has an image of a permutation. So G is said to be a Frobenius group. Frobenius, actually. If the following hold. The first property is that G is transitive. Okay, so this means that there is a unique orbit. So G has a unique orbit. On omega. And recall that this implies that all stabilizers are conjugate. Because there is a formula that we'll be using that says that if you have a stabilizer and you conjugate with G, this is the stabilizer of alpha G. So since G has a unique orbit, every stabilizer is a conjugate of a fixed one, okay? The second one is G alpha different from 1. And here you can quantify as you prefer. I mean, you can say for all or for one, because they are all conjugates, say for all alpha in G, in omega, okay? And the third property, which is the serious one, says that for alpha and beta in omega, if alpha is different from beta, then, well, it might well be that in an arbitrary permutation groups, a group of permutation and set omega, the stabilizer of two different points are the same. But here we require not only that they are different, but actually their intersection is trivial. Where for subgroups, the trivial intersection means that the intersection contains only one. And okay, so it's quite a strong property. So it's transitive. The stabilizers are not trivial. And two stabilizers with respect to distinct points are not only distinct, but have trivial intersection, okay? Let's give examples of this. And there are two examples that you know very well. Okay, so the first example is the following, is S3. Okay, of course, S3 is a group of permutation on the set 1, 2, 3. Okay, actually, it's the group of permutation on the set 1, 2, 3. So my omega is the following. Okay, let's call it G. Otherwise, when I write the stabilizer, we get a mess. So what are the stabilizers? So the stabilizer of G1 is 2, 3. Is the subgroup generated by 2, 3. The stabilizer of 2 is the subgroup generated by 1, 3. And clearly enough, the stabilizer of 3 is the subgroup generated by 1, 2. And you see that the pairwise, they have trivial intersection, okay? So this is a Frobenius group. So example A, say. Example B is A4, okay? So A4 is a subgroup, this time a subgroup of S4, so a group of permutations on 1, 2, 3, 4. What are the stabilizers? Well, one see immediately that the stabilizer the stabilizer of 1 is generated by 2, 3, 4. The stabilizer of 2 is generated by, of course, is transitive, okay? Well, why is it transitive? Because just you consider I went back to S3 here, because if you consider the subgroup generated by the cycle 1, 2, 3, of course, this brings 1, 2, 3, and then this back to 1, okay? This is also transitive, A4. And you can consider the group formed by the product of two disjoint two cycles. Okay, and this is clearly transitive because this brings 1 to 2, this brings 1 to 3, and this brings 1 to 4. Okay, so it's transitive. It has even a transitive subgroup. So we'll finish here. This is the stabilizer of 2, this is stabilizer of 3. And finally, you get the stabilizer of 4, which is just 1, 2, 3. And you see clearly that they are of prime order, and so either they coincide or they have a trivial intersection, so they must have trivial intersection. Okay, so this is an example. But let's come to this definition, and we'll note a consequence of this definition. Okay, yes. So if G is a Frobenius group, finite one, I should say, then H equals G alpha is called a Frobenius complement. Okay, so any of these G alpha stabilizers is called the Frobenius complement. Claim if H is a Frobenius complement, in G, then H is self-normalizing. The normalizer is itself. Why is it so? Well, suppose proof. Suppose X is in the normalizer of G alpha. Okay, so a Frobenius complement is one of these G alpha. So this means, this is equivalent to say that G alpha conjugate, this is the conjugate, okay, equals G alpha. But by the formula that I recalled earlier, this conjugate is its stabilizer itself, is the stabilizer. Now let's write it, I'll write it here, is the stabilizer of alpha X. So we have that the stabilizer of alpha equals the stabilizer of alpha X. But if you look back at the definition says that if you have two different elements, then their stabilizers are disjoint. And here you have two elements, alpha and alpha x, which have the same stabilizer. And recall, another condition is that this is different from one. Let's go back a second. Stabilizers are different from one. So here you have two stabilizers. There are not only they don't have a trivial intersection. They are actually equal. Okay, it follows that alpha equals alpha x. Let's recall why, because if alpha is different from alpha x, then G alpha intersect G alpha x. This is one of the conditions we had, has to be trivial. Whereas in this case, the intersection is G alpha, which is not trivial, okay? Whereas in this case, the intersection is G alpha, which is different from one, okay? So what have we obtained? We have obtained alpha equals alpha x, but this means exactly that x is in G alpha, okay? So we started with an element in the normalizer of G alpha, and we ended up with showing that x is in G alpha. And we obtained this by playing around with the two properties, which I'll recall once more because we get to get familiar of Frobenius group, that G alpha is different from one, and then if you have two different elements in omega, their respective stabilizer have trivial intersection. Okay? Okay, so this is important and will play a role later, but what we have from the definitions, if G is a Frobenius group. Sorry, I will switch back. I'm switching back and forth between two pronunciations. The correct one is Frobenius because it was of German birth. But when one speaks English, it's usually to call it Frobenius, which is wrong, but I mean, as it happens. So if G is a Frobenius group and H is a Frobenius complement, okay, so this means it's a one-point stabilizer, then we have that H intersect Hx equals 1 for x not in H, okay? And the reason is what we have just seen, because the reason, in fact, if H is G alpha, okay, and X is not in H, since we have proved that the normalizer in G of G alpha is G alpha itself, then this means that G alpha X, the conjugate, is different from G alpha, okay? And if it's different, of course, it must have a trivial intersection, because this is not in H that G alpha intersect G alpha X. So it has to be 1, okay? Since they are different, this means that alpha is different from alpha X. And so the intersection has to be trivial, okay? Let's close the parenthesis. So once more, if H is a stabilizer of G alpha and X is not in H, then this is different from G alpha because X does not normalize alpha. And so, of course, this means that since this is G alpha X, this implies that alpha is different from alpha X, otherwise the two will be the same. And then this intersection, which you can write in two ways, with the X up or with the X down, has to be trivial by the axioms of Frobenius groups, okay? So the second definition, let's see how Okay, definition 2. A finite group G is a Frobenius group if there is a subgroup H different from 1 of G, okay, such that H intersect HX equal 1 for X not in H. Okay, well, this actually works even for infinite groups, but we'll stick to the finite case for the sake of characters. So the second definition is this G is a Frobenius group if there is a non-trivial subgroup H, such that the intersection of H and any conjugate is 1 when X does not lies in H. Of course, we have just proved that definition 1 implies definition 2, where definition 2 requires a subgroup H with certain properties, and the subgroup H, once you have definition 1, is exactly G alpha, okay? Any stabilizer. Now let's prove that definition 2 implies definition 1. So perhaps I could copy this definition. Yes. Well, I'm not sure what happens if I do that, so let's not do it. Okay, so definition 2, let's recall. So you have a subgroup different from 1 with the property that H intersect HX is trivial if X is in G but not in H, okay? So definition 1 requires to have a set on which G acts. Actually, such that X is G is a permutation group. It's contained in the it's a permutation groups on omega. So our omega will be the set of right cosets of H in G. Okay, the set of right cosets of H in G. So G, of course, acts transitively on omega by right multiplication. Okay, why transitively? Because if you multiply A by A inverse B, you obtain HB. So you can take any coset to any other coset by multiplying by this. Or you could prove, of course, that the orbit of H is everything, because it's simpler if you multiply H by A, you obtain HA, of course. It's even simpler because you just have to prove that the orbit of one element is everything. Good. What are the one-point stabilizers? Well, you know that the stabilizer, this is something we know from the first course in group theory, the stabilizer of the coset, HA is nothing else that H, the conjugate, okay? I won't repeat the simple proof, but one knows that this holds. And of course, since H is different from 1, all of these are different from 1, which is another condition that I needed. The last condition I need to prove that to stabilize, if two elements, yes, I want to prove, so far G acts on omega. What is the kernel of the action? Because remember, this action gives us, or is equivalent to, let's write it better. a morphism from G to S omega, to the group of permutation on this, in which an element, say G of G, goes in the permutation, we send HA to HAG. Okay, so it's a morphism, but one knows. Let's call it F. This is not dangerous, and it's known that the kernel of such a morphism, in general, as you know, actions, group actions can be given either by two axioms or in this form as a morphism from G in S omega. And the kernel of the action is nothing else by the intersection for all G in, just a second, for all alpha in omega, of the stabilizers, G alpha, okay? Because an element G is in the kernel, so it goes to the identity. If let's say, general form is alpha to alpha G, if it sends alpha to alpha for all alpha, it means it's the identity, okay? So the kernel is the following. And in this case, what we have, since the stabilizer are disconjugate, this is intersection A in G of the conjugate H to the A. But you see, it's enough to take two of these to have that this is one. Okay, it's enough to take A equal 1 and then A different from 1. Okay, and then H intersect H to the A will be 1. Okay, so just the intersection of two is trivial, so this is trivial. And so this proves that the kernel is trivial. Since the kernel is trivial, I recall that this is the formula. What we obtain, we have that the morphism F is injective. And this means that, so G is, well, not right a subgroup, but isomorphic to a subgroup of S omega. So it's the usual thing. It's not that G is exactly a subgroup of S omega, but this is, since this is injective, the real subgroup is F of G. But of course, it does not make any difference. I mean, G, I mean, replace G with FG and you are there. So this is injective, so FG is isomorphic to G, okay? Good, and the last condition we have to prove, the last condition, which says that if alpha is different from beta, these are elements of omega, sorry, not of G. These are elements of omega. Then G alpha intersect G beta has to be 1, okay? So in this case, we take two cosets, okay? And we have to prove, okay, let's put it this way, to be proved, so a big question mark, that the stabilizer, the two stabilizers have trivial intersection, okay? Okay, but what's the stabilizer? Well, we know because we just, okay, this is, as we said, this is the conjugate of A intersect the conjugate. Say H conjugate through A intersect H conjugate through B, okay? Remember that the assumption we have is that H intersect H to the X is trivial if X is not in H. So to get back to this situation, we simply do the following, sorry. Okay, so we have just, H is horrible and I will replace it. we have simply pulled A out, so A has disappeared here, and here you have B, A minus 1. But the point is, since remember that A equals HB if and only if, this is the relation that builds the cosets, if and only if H equals this, okay? That is if and only if BA inverse is in H, okay? So two cosets are equal if and only if this product is in H, okay? Now, these cosets are, this is an if and only if. These cosets are different. So this means, this is equivalent to saying that BA inverse is not in H, okay? And if this is not in H, by the assumption we have here, the intersection is trivial. And if you conjugate the trivial intersection by A, you get 1. So what we obtain, in fact, that the intersection of two that if you have two different elements of omega, which is the set of right cosets, then the intersection of the two stabilizers is trivial. Okay, just by invoking the previous this axiom. Good. So let's okay. Now, what does Frobenius theorem says? Well, note, consider the examples again. The two examples I gave. Okay, S3. Okay, so you have the Frobenius complements. So say one of the Frobenius complement is, for instance, the subgroup generated by 1, 2. Okay, and note that S3 is a semi-direct product, internal semi-direct product of subgroup generated by 1, 2, 3 by the H. Of course, S3, this is a group of order 3, this is a group of order 2. So this is, of course, normal in S3. And so it's a semi-direct product. And moreover, you can note that the subgroup generated by 1, 2, 3 can be obtained from S3 in this way. You first take out the union of the stabilizers. Okay, so the stabilizers are 1, 2. This is a set theoretic union, okay? But then, of course, you have to add 1 because you took away 1, okay? So 1, 2, 3, so the S3 has 1, 2, 3 here, the generated by 1, 2, 3, and this 3 stabilizer. So if you take away the 3 stabilizers and add back 1, you get this, okay? And the same thing happens with A4. Because in A4, you have here the subgroups formed by 1, and then the product of the two disjoint 2 cycles. And then you have the stabilizers here, 1, 2, 3, and so on. So once more, there is it's called the subgroup V, okay? So V, which is the subgroup, okay, let's rewrite it for clarity. This subgroup is a normal subgroup of A4, okay? And is obtained from A4 if you take out the stabilizers and add back 1 because you have taken away the 1 several times. So the stabilizer, union of the stabilizers. And once more, A4 is a semi-direct product. of V, this normal subgroup, by one of the stabilizer. Okay, let's say 1, 2, 3. Okay, stabilizer. Okay, so we will say that, let G be a Frobenius group, H a Frobenius complement. So you can think of H in two equivalent ways. Either one of the stabilizers, if you think of the group as a permutation group, or as a subgroup such that intersection with the conjugate is trivial. Okay, then a subgroup K of G is called a Frobenius kernel if the following hold: K is normal in G, okay? And let's put it like this. K intersect H is trivial, and 3, G equals HK. So what we are saying here, we are saying that G is the semi-direct product of K by H, the internal or inner semi-direct product, okay? We have seen in the two examples, so both S3 and A4 have a Frobenius kernel. And the important theorem of Frobenius says the following: let G be a finite Frobenius group. Any definition, either definition 1 or definition 2, then G has a Frobenius kernel. Okay? So I think I'll give the proof tomorrow to keep it all together. But let me finish today by finding a natural candidate for this Frobenius kernel. Okay, is the following. So G is a Frobenius group. So let G be a Frobenius group with complement H. So we do exactly the same thing that we have done, we have noted in these two examples. Consider the set N, which is given by, you take G, you take out the union of all conjugate of H, and you add 1. Okay. So what is obvious is that N is a normal subset of G, meaning that you don't know there is a subgroup yet, meaning that if N is in N and X is in G, then the conjugate NX is in N. And the reason is rather trivial, because there are two possibilities for an element of n. Yes, this time I'll make a copy. No, this one. Add to next new page, okay. Because you see, consider first the case when n is 1, okay? Then, of course, if x is an element of G, then, of course, nx is 1x equal 1 is still in n. So if n is in n, but n is different from 1, okay? Then what we have is that n, since it's in this complement, n is not, okay, I should be careful with the letters. Okay, let me change this letter. Let's call it y here, okay? So I've changed all these letters here to y in this, let me circle them so that you see what I've changed quickly. Okay, so let y be in G, okay? Okay, fine. Then we know that n is an element of G which is not in any conjugate of x for all x in G, okay? But then if you conjugate by y, you obtain that this is not in the in xy for all x in G, okay, because I've just conjugated both sides. And of course, say y is fixed, and once you fix y and you let x range over G, this is an arbitrary element. So what you obtain ny is not in hz for all z in G. It's the usual fact that once you fix x, the map, the y, sorry, the map that sends to x to xy, so fix y, then this map is a bijection. I mean, it's right multiplication by y, okay? So if n is in n and is different from 1, then n is not in any conjugate, and then none of its conjugate are in a conjugate of x. So it stays there. So n is a normal subset, and claim, this is the claim that will be proven tomorrow, n is a subgroup. And thus, it's the required Frobenius kernel. So it's obvious that it's a normal subset. That if you take an element and you conjugate, you obtain another element in n, but what will be proven tomorrow is that it is a subgroup. And let me take a few more minutes to explain briefly what's the idea of the proof. I'll first recall a general fact. And the general fact is the following, that I'm not sure whether I have ever quoted it, but I'll prove it tomorrow. You see that it follows from things that we have already seen. So the first thing is that, that if you have a group H, and it will be clear in a second why I'm taking exactly a group H, then the intersection if you take the intersection as chi ranges over the reducible character, finite group, chi ranges over the reducible character of the kernel of chi, this is trivial, okay? We'll prove this tomorrow, okay? And and we'll recall also what the kernel is and so on. But since in any finite group, you have the trivial character. This is the first line in a sensible character table, the line which all ones. Then the kernel of 1H is H, okay? Yes. Yes, the kernel is H. And so you can even say, so H, so the trivial kernel does not contribute to this intersection because you are intersecting object that is a subset of H, and this is H. So all you know that so far, if you take just this kernel, is that is a subgroup of H, which you knew from the start. So if you can even take chi different from the trivial character, and you still have that the intersection is 1. Because I mean, this kernel, the kernel of the trivial character does not contribute anything. So this is the first step. If you have a finite group, we'll prove it tomorrow, although it follows from things that we have seen. This intersection is trivial, okay? But then the idea will be that if we are able, okay, the idea will be a heuristic argument, okay? If G is a Frobenius group with a complement H, okay, and kernel K, so we are assuming it has a kernel. Okay, so G is a semi-direct product H K, and we know that if you consider G over K, okay, this is HK over K, by the second isomorphism theorem, this is isomorphic. Say there is an isomorphism to H over H intersect K, but this is a semi-direct product. So this is trivial, okay? And this is isomorphic, say, to H, okay? So you have an isomorphism from G over K to H, and call this isomorphism F. Then any character, in particular irreducible character, of H extends to a character of G. Because if chi is a, let's say, a irreducible character of H, okay, then you can define chi of an element of G, say chi prime, as chi of f of G. Okay, so because the idea is you have the character, which is a function from A to C, or the representation, and here you have the function f. Okay, so you compose the two, and you obtain a character, is a character of G. And if you put together this with the previous fact, okay, you obtain, I'll repeat this argument tomorrow, you obtain that this kernel K will be the intersection of this of the kernel of this K prime, where as chi ranges in the reducible character of H, sorry, different from 1H. Because of this extension, because I mean, if you consider this map, of course, of course, K is in the kernel, and so so Fk, say K is in the kernel, K is exactly the kernel of F. Okay, so when you apply F to an element of K, you get 1, and so you'll get something in the kernel of Chi prime. And so the idea will be to find a way. So this is a heuristic argument. So we are assuming that this kernel exists. What we'll do tomorrow, we'll find a way to extend the irreducible character of H to characters of G, and then the required kernel will be the intersection of all these kernels. But I'll resume, I'll reprise this explanation tomorrow, and we'll give the proof, which, as I said, is an interesting application of induced function more than induced characters. Okay, so that's all for today. Thanks a lot.